محاضرة اليوم مناقشة الدكتوراه اللي قد كان قاسم زيرك. عنوان الأطروحة هي Evaluation of aerosols effect on the efficiency of solar power plants in Algeria. Qasim, you have 30 to 35 minutes to present the essence of your work. Please.
Dear parents, respectable Professor Kacem ZEREG, President of the jury, Honorable jury, kind audience, thank you for your welcome assistance. Today I'm going to present the essence of my doctoral thesis entitled Evaluation of aerosols effect on the efficiency of solar power plants in Algeria. As for my presentation, it is planned to go through the following contents: introduction, theory and terminology, methodology, results and discussion, and finally conclusion. First, with the introduction, where I will explain briefly the context and motivation of the present thesis, as well as the objectives of our research. Next, in theory and terminology, I will explain some concepts that are needed for the good understanding of the established work. After that, the methodology followed to conduct our experimental research is explained. Then comes the crux of the matter, which is the presentation, explanation, and interpretation of the obtained results. Finally, I will end my presentation with the conclusion. So first with the introduction, where I will explain the context, motivation, and objectives of the present thesis. After the lift of the COVID-19 travel restriction, the resumption of industrial activities, and the overconsumption of coal due to Russian-Ukrainian conflict, fossil fuels consumption is increasing uncontrollably. Indeed, the main sectors responsible for greenhouse gas emissions are electricity and heat production sector and transportation sector. Due to the unprecedented records of high temperatures, the United Nations declared the passage from global warming to global boiling, especially with the environmental impacts and natural disasters. Here we can visualize the increasing global temperature during the last 150 years. Due to these reasons, the energy transition from fossil resources towards renewable, sustainable ones is necessary now more than ever. Among renewable energies, solar energy is an abundant one and leading the process of energy transition. The most major solar energy applications are photovoltaics and concentrated solar power plants, shortly CSP. CSP replaces fossil fuels combustion by the heat converted from the massive concentration of solar radiation. The most advanced CSP configurations are solar tower, parabolic trough, linear Fresnel, and parabolic dish. Our focus will be on the solar tower thanks to its possibility of reaching temperatures higher than 1000 degrees, which means the potential of enhancing the efficiency of electricity production. The components of a solar power plant are the solar field, the optional thermal storage block, and the power conversion system or the power block. Our focus will be on the solar field since it's the component concerned by dust problems. The Algerian Sahara has an important potential for hosting solar power plants. However, the presence of the Saharan dust would reduce considerably the efficiency of electricity production, which motivates the present thesis. Especially with the increasing interest in CSP technologies in arid regions, which is reflected by the fact that CSP dust problems is a research trend. Our motivation was deepened by the fact that even though soiling is a common problem for PV and CSP, at least 5 experimental studies of PV soiling were published, while no CSP soiling research was conducted, which would make the present work a first one in this context. The objectives of our research are the following. the establishment of the first literature review of dust impact on concentrated solar power, and with the conduction of the first outdoor experimental research on optical losses due to dust deposition on heliostats under Algerian climate, and finally with the assessment of an anti-soiling coating as a mitigation to this issue. In the second part of my presentation, theory and terminology, I'm going to explain some basic concepts and parameters that will be used to obtain the experimental results, namely the optical efficiency, reflective efficiency, and atmospheric attenuation. First, with the optical efficiency, which is the ratio of the received radiative energy to the total reflected radiative energy. The optical efficiency can also be expressed through multiple factors reflecting various sources of losses, such as reflectivity losses or reflective efficiency, atmospheric attenuation, losses due to cosine effect, shading effect, so on and so forth. Efficiencies that are concerned by dust and aerosols problems are the reflective efficiency and the atmospheric attenuation. The reflective efficiency is based on the key parameter of the reflectivity, which is the ratio of the reflected irradiance to the incident one. The reflective efficiency of a solar mirror is its reflectivity in its solid state and is expressed as a function of its reflectivity in its clean state and the percentage of the remaining clean surface. The cleanliness index provides a better display of the impact of dusting on the optical efficiency. The reflectivity of the soil mirror divided by its reflectivity in its clean state. So here, it's kind of, we are taking the reflectivity of the mirror in its clean state as the reference instead of 100%. While soiling rate reflects better the impact of the site's arid climate on soiling intensity over the exposure period. Regarding the atmospheric attenuation, it is expressed as the ratio of the values of the direct normal irradiance D and I at the border of an atmospheric layer, and is a function of the solar zenith angle and the optical depth of that atmospheric layer. The atmospheric attenuation due to aerosols can be expressed using either of two formalisms, the formalism of angstrom and the formalism of Link. For the formalism of angstrom, aerosol's optical depth is a function of angstrom's coefficient beta, which reflects the quantity of aerosols in an atmospheric column, angstrom's exponent alpha, which is inversely proportional to aerosol's particle size, and the wavelength lambda. For the formalism of Link, the optical thickness due to aerosols is expressed through Link's turbidity factor TL. Physically speaking, TL is the number of the clean dry atmospheres required to reproduce the effect of the hazy turbid atmosphere. Now for the methodology of our work. Of course, starting from the description of the exposure site, the installation of the experimental setup, to the measurements of reflectivity and dust weight, and finally with the characterization of the deposited dust particles. The outdoor exposure took place in the city of Lagouat, and more precisely next to the Faculty of Technology of the University of Lagouat. Previous climatic data during the month of June are presented here. The average monthly global horizontal irradiance GHI was about 560 watt-hours per meter square, while the monthly wind speed and relative humidity were 4.4 meters per second and 32.3% respectively. Here we can visualize the hourly data of the representative day for each climatic parameter. So the representative day is the day of which the daily average value is the closest to the monthly average. For the global horizontal irradiance, its values were greater than 500 watt-hour per meter square during 8 of the 11th daylight hours, which reflects the site's potential to to host solar power plants. 25% of the hourly data of wind speed were greater than 6 meters per second, which indicates the potential of the erosion of mirror surface at the exposure site. The relative humidity was most important in the early morning and night time, which makes this span of day maximum for soiling risk, especially that it might coincide with strong wind, as can be seen here. 20 times 25 centimeters square sample mirrors were self-exposed composed of 2 rows with 50 centimeters of height difference. The lower row was used to study the effect of tilt angle, and 4 mirrors were fixed at different tilts of 0 degree, the horizontal, 15 degrees, 30 degrees, and 45 degrees. As for the upper row, it was used to study the effect of coating in mitigating soil issues. 2 mirrors were fixed at the horizontal and the other 2 at 30 degrees. A mirror of each inclination was coated and the other one left uncoated in order to assess the efficiency of coating in reducing soiling intensity. These photos were taken during the installation of the experimental setup, where we were working under temperatures higher than 40 degrees during the month of June. For reflectivity measurements, first the illuminance of the sunlight was measured using a lux meter, then the illuminance of the reflected light was also measured, and the reflectivity was determined from their ratio. In order to assure the precision of this procedure, we repeated the same operation at the Laboratory of Engineering and Systems of Versailles by measuring simultaneously the radiance and the illuminance of from a reflected mirror using a reflectometer and a pyranometer. The comparison revealed a very low relative error of 0.3%, which confirms the precision of the procedure followed here. Furthermore, the procedure we used requires a more available device, which is a portable reflectometer, which is also more practical. To determine dust weight, first we measured the weight of a clean wipe, then the weight was measured again after cleaning the dust off the surface of the mirror. The weight of dust is the resultant difference. 2 high-tech devices are used for dust characterization. The first one is a high-resolution scanning electron microscope capable of studying samples in their natural state. The second one is a 3rd-generation intelligent diffractometer that determines the structure, composition, and properties of materials by X-ray diffraction. Now for the most important part, where I will present and discuss the obtained experimental results. So first, with the effects of tilt angle, coating application, and height difference on the intensity of soiling, then with the physical interpretation of the obtained results, and finally with the physical and chemical properties of the analyzed dust. So, following 74 days of outdoor exposure without any cleaning, be it manual or natural, which means rain, we can see here that the intensity of soiling is most important for the horizontal mirror and decreases with increasing tilt angle until it reaches its minimum for the 45 tilted mirror, or the mostly tilted mirror. Another factor of optical losses was detected, which is bird droppings that were depicted on one of the exposed mirrors. The performed measurements confirmed the visual inspection. Dust deposition rate and tilt angle are inversely proportional, while the latter is proportional to soiling rate. Since the negative sign of soiling rate stands for the losses in optical performances, the intensity of soiling rate is inversely proportional to tilt angle, similarly to dust deposition rate. The horizontal mirror logically had the most important dust deposition rate of 8.65 centigrams per meter square per day, and the minimum dust deposition rate was 2.16 centigrams per meter square per day, characterizing the maximum tilt of 45 degrees. Consequently to this, the horizontal mirror had the most important soiling rate of minus 0.99% per day of soiling rate, and the minimum was 0.9% per day, characterizing the 45 tilted mirror. Coating as a passive mitigation for soiling has been tested. Coating is sustainable in terms of water resources and economic in terms of avoiding active cleaning. The coating's diminution of soiling was more important for the tilted mirror than for the horizontal one. Indeed, the diminution in dust deposition rate for the tilted mirrors was 1.62 centigrams per meter square per day for the coated mirror when compared to the uncoated mirror. Consequently to this, the coated mirror had a cleanliness gain of 0.08% per day, which would be the equivalent in 10 days of 1% of cleanliness gain, which is an important gain. For the horizontal mirrors, the coating resulted in a slight optical gain. The coating is still of benefit, even though the benefit is not as denounced as for the tilted mirrors. Regarding the height difference, and as can be seen from the side view schematic of the experimental setup, there is a 50 centimeter height difference between the upper and the lower row. Since each row has two mirrors of identical tilt and state of surface, namely the horizontal and 30-degree tilted uncoated mirrors, we thought about the study of this effect on the intensity of soiling. Of course, one would expect that the lower mirrors would accumulate more dust than the upper mirrors, which is truly the case. So the dust deposition rate for the tilted mirrors was more important for the lower mirror or the bottom mirror than the top one. And the same can be said regarding the horizontal mirrors. Furthermore, the difference in the deposited dust between the upper and the lower mirror was more important for the horizontal mirror when compared to the tilted mirrors. As a consequence to the more deposited dust on the bottom horizontal mirror, it had more optical losses. While for the tilted mirrors, the bottom mirror had a slightly better optical performances than the top mirror, so the lower optical performances of the top mirror might be due to some unevenness in the distribution of dust particles. Since when we measured the reflectivity, we measured it at different spots and then averaged the values. Physically speaking, this difference in optical behavior might be due to the fact that the soiling of horizontal mirrors is mainly due to the gravity force than to adhesive forces. While for the tilted mirrors, the perpendicular component of the gravity force contributes to deposition and settlement of dust particles, and the parallel component contributes to their removal. Coating the reflective surfaces of the mirror weakens the adhesive forces and enhances the removal even further. The intensity of removal is proportional to tilt angle. Now for the analysis of the size, morphology, and chemical composition of randomly picked up deposited dust particles. The characterization was done by scanning electron microscopy, energy dispersed X-ray spectroscopy, and X-ray diffraction. The particles size was lesser than 120 microns. And regarding their morphology, more sharp and angular dust particles are present than round ones, which explains the important optical losses. Both of these findings regarding the size and the morphology of dust particles are in consistency with previously published papers. For X-ray diffraction analysis, the main components are quartz with 50%, calcite with 30%, which means that both made up to 80% of the chemical composition of the deposited dust particles, which is also in consistency with the literature of the matter at hand in arid desertic regions. For energy dispersed X-ray spectroscopy, the dominant elements of the deposited dust are oxygen, carbon, silicon, iron, calcium, and potassium. Thus, the origin of dust is both natural and anthropogenic, which is logical since the site of the exposure is situated at the outskirts of the city of Rawat near a surrounding mountain. Thus, this mixity in origin of dust particles. To conclude my presentation, I will provide a graphical abstract of the experimental study, followed by the main highlights of the present thesis, and finally with the perspectives of the present work. So first, with the graphical abstract of the conducted research. So clean mirrors were exposed on an experimental setup, and after 74 days, their reflectivity was measured in their dusted state. The studied factors are the tilt angle effect, the coating effect, so the mainly effects that were studied, and of course the physical and chemical analysis of the deposited particles was performed as well. As for the main highlights of the present thesis, so the obtained results are in accordance with the theory and the literature of the matter at hand. The intensity of soiling is inversely proportional to tilt angle and height difference, and the application of a protective coating is of positive effect in mitigating soiling intensity. The present study is valid for all CSP technologies since the mechanisms of dust deposition and optical losses are the same for all of them. Sloping solar mirrors at an angle, no matter how slight it is recommended in order to avoid the maximum soiling intensity that characterizes the horizontal mirrors. Finally, soiling as a confirmed source of optical losses should be assessed during the design phase of solar power plants in particular and concentrated solar power plants in general. And this in order to have a good estimation of the produced energy and avoid any unpredicted losses. Finally, with the perspectives of the present work, we think about the establishment of the first cartography of atmospheric aerosols content in Algeria, and also the assessment of the efficiency of electrodynamic screens, shortly EDS, in mitigating the soiling intensity under Algerian Saharan climate. Thank you for your attention.